Thank you very much. So, good afternoon once again. I'm kind of like changing roles to present some work that we have been doing over the past 3 years in a framework of a national European project that is co-financed by Greece and the European Union ERDF program. The main author, Elena was not able to attend, so I have the privilege of presenting this work. The first question, maybe by reading the title, you preparing yourself of the area, the topic of residential buildings. So we're focusing on residential buildings for a very good reason. They represent about 30% of the total final energy use, so about a third. You may have think that I've mixed up my numbers because you've been hearing the 40%. That represents like the entire building stock. So talking about residential buildings, the millions of buildings, the billions of floor areas that operate out there, and you look at the picture here of the real data from the energy use balance statistics of the European Union. Point of caution though, you see the note on the left right here. Indoor environmental quality is always an issue when we look at real energy use, and that was kind of like brought up in the previous presentations. So these are the numbers. This is how much energy we're using. And of course, we had an excellent introduction. You all are aware of the emphasis we've been placing on reducing the energy use as a main priority. Energy efficiency has been at the top of European policy efforts. So we are driving our new buildings towards NZEBs, towards nearly zero energy buildings. The energy use intensities indicated in this graph, again, illustrate the big differences among the different European countries. And what is more alarming is not when we're down here, but when we're up here in the countries that not only have a higher EUI, but also the buildings represent a big part of their final energy use. So there is a big burden. So you see, as we move at the higher end, and we reach to over 30%, as we said, that's about the average in Europe, there's a group of countries that they actually need to focus and put as a priority to renovate the existing building stock. Now, what we do and how we deal with the millions of buildings that we have, depending on location, depending on vintage, the period of construction, and the type, this combination we have, and we are focusing on the single-family residential buildings in this analysis. So we do have lower EUIs. There is progress. There are now, this is a reality in most European countries that for our new buildings, it's common standard construction. Otherwise, if you are not an NZEB, for public buildings, we have already started. For next year, for every building, you simply won't get a building permit. So that kind of addresses the main issue, solving the problem for new buildings. But what about existing buildings? Now, already with existing buildings, we have invested a huge amount of energy and a lot of other values in terms of their construction, but also their operation needs not only operational energy consumed, but the addition, replacement of some building components, some building systems. Now, it takes energy to produce these building components, and that we refer to as embodied energy. So from day zero, when you get a boiler at your house to replace your own one, there is already energy being spent to produce that unit. You replace your windows to reduce your operational energy use. already the windows you bring in have some embodied energy, and already the ones that you're throwing away, and hopefully recycle if they're recyclable, have some energy included. So overall, when we take into account the amount of energy from the extraction of the raw materials down to delivering it to our building, this part of the energy is referred to the cradle to gate and represents about 92% of the total energy. And if we get it to our building, that's an additional 7%. So altogether there, that's kind of how much energy is already embodied. And every time we renovate, every time we replace an old building component or we add something to the building, in order to move to lower EUIs, to lower operational energy use, we increase the embodied energy. So that kind of, as we think of EUIs for operational energy, the embodied energy intensity, the EEI, is something similar to think about in terms of comparing. So part of the work that we did was to, first of all, increase our knowledge base of how much energy is produced, not according to the international databases, but according to local national practices. So we built a better understanding for different materials, for different components, to calculate the embodied energy intensity, and then assess different popular energy conservation for our buildings. The first thing that we did was to collect some locally applicable information. So there were short energy audit surveys of different manufacturing facilities to collect the relevant information. And one of the main things that we learned, we were expecting it will take time. What we were not expecting is that this will be considered as proprietary information. There were factories, production sites, and so forth from the bigger ones primarily. They refused to release that type of information. And of course, while we have the different requirements in different countries with regard to EPBDs, some have produced these. They should be public, so we took advantage of that, but still, because they're on voluntary basis, they're not always available, so that's something to look at. So we do have this information about the embodied energy coefficients that we have collected for the different materials, and then the other part of the calculation process is to assess how much of these materials do you have in your buildings. To answer this question, of course, you cannot consider every single building, but as we do for these large-scale applications, we consider different case studies that cover different construction periods that are typical, representative of the construction practices that we have for the four, as you see there, periods in Greece with regard to our houses. And what is interesting, and that's what usually happens, is that when you look at the different materials that you have on a mass basis, well, that doesn't tell you the full story unless you combine it with the embodied energy coefficients, because a small amount of material with a very high embodied energy coefficient may result, as you see, for values that actually have a major impact on the overall embodied energy of the building. On the other hand, if there is a material with a very high embodied energy coefficient, when you combine, with a very low embodied energy coefficient, if you combine it with materials that are maybe low in quantities, the end result may again have a contribution to the total. So doing this exercise for the four typical buildings, these are the results using the software that's available to do a life cycle analysis, using our field data, national adopted data, and so forth. And you see the results there using the new knowledge that we had and the available information data in the international databases. So this is giving us a feeling of how much off you will be if you had the calculations performed by and using these internationally available tools. Overall, we saw about 15% differences from the exercise that we did. So now we start having the first EEIs, these first indicators, ranging, as you see, from 3.2 up to over 7 gigajoules per square meter floor area. We have an average of about 5.6 gigajoules of embodied energy. So if we kind of like scratch now and compare the operational with the embodied energy. We did this exercise by placing our 4 typical buildings around the 4 different climate zones that we have in Greece, considering a 70-year lifetime of the building, and looking at the total embodied energy to the total primary energy that includes the operational and the embodied for the lifetime of the building. And what do we see? What you usually expect is that it is not that important once you're looking at the old buildings. That embodied energy would represent, with the high energy use of the old buildings, about 1.5%. But if you look at the more energy efficient buildings, the buildings that have been constructed over the past decade, and even more as we move to the nearly zero energy buildings, the embodied energy of the materials of the system, the components of the building, will have about and represent about a third, as you see on the overall balance that they will have. Now, all buildings will require some kind of renovation, so we did the exercise of assessing some popular energy conservation measures. For example, replacing your boiler. For example, putting new double-glazed aluminum frame, popular interactions in Greece, or adding insulation, or adding solar collectors for your domestic hot water, or combining. And you see the results there of the recovery period. What do we mean by that? How much time it will take to recover the energy already embodied in the new material that we, or systems that we bring into the buildings, compared to the energy savings. So you see, on average, that would range from 1.2 to 3.1 years. Okay, that's not striking, but there's someone there kind of like thinking, these are calculations, but actual energy use, as we've heard, can differ. So what a calculation may tell you that you will save in the operation of your building may actually be lower in real life, not be able to achieve. So in that case, what we have been trying to look, and this is the approach we have been using, is to look at the actual energy use compared to the calculated with the tool, the calculation engine that we are using in Greece. Not to judge how accurate or how good or how bad it is, for better or for worse, this is the calculation engine that we have in Greece. But more than anything else, look at the divergence from the real world from the calculated. What we primarily see in our observations from these results is the well-known pre-bound effect, which is telling us that we are actually using less energy from what we're calculating for many various reasons, ranging more than anything else from the operation hours, for the systems, efficiencies and performances and so forth, but the role of the occupant is the dominant factor driving this. Doing and repeating now the exercise under this adapted values for the actual energy use and performance, you see the equivalent results, which shows then the embodied energy in real terms of how much energy you will be saving during the operation of the building. It's going to take about 2 to 5 years to be able to recover the energy that has been embodied, again, in the components of the systems that we have been using. So in conclusion, we're trying to look with this kind of work, the role of the embodied energy especially as now we're getting into the era of the low energy performing buildings. The decisions of what materials, what systems we will be selecting, using and installing in our buildings becomes, as we say, even more important. Now we are trying to build and enhance our knowledge base with more data with regard to this information on the national basis. This is a process that every piece of information data added is a valuable one. And we're going to be also looking and expanding, in addition to the single family, to the multi-family, and then different non-residential uses. And of course, one of the main things, and we have been hearing and getting this information, that the new standards and the new regulations are already looking and focusing, and you in your professional world practice, you should also be becoming more aware of making better choices and using better systems, better materials for our buildings, so that we can secure, alongside of lower EEIs, but more than anything else, secure, healthy and sustainable buildings. Thank you very much.